Okay, so this video is going to discuss what up until this point I've been referring to as transfer function coefficients, but don't specifically have to be transfer function coefficients. So this vector here, b0, b1, b2, a0, a1, and a2, I've talked about at length, using those to implement some frequency response characterization of a system. But we can also use those coefficients in the time domain to generate an impulse response, which is generally the time domain characterization of a system. So we use large H generally to represent the transfer function, which is the frequency domain characterization of a system, and we generally use small h to represent the time domain representation, which is a impulse response. So h of e to the j omega here, this is e to the j omega is just our frequency vector, so for a bunch of different points in frequency we have h defined as the division of the output y by the input x. And that means that whatever arbitrary stimulus x is, the specific spectra of x will be divided out, and it won't matter, and h will always be constant. So whether x is pink noise or brown noise or white noise, the spectrum of x will be divided out, and so h is always constant. Now this function here, to compute the transfer function directly, I've talked about a lot, but we can, as I just said, use these coefficients instead directly in the time domain. And the kind of shortest hand way to write that is here. But if we have three coefficients, then this equation breaks out here where we have a0, a1, and a2 on the left as coefficients to this y vector, and so now this is lowercase. We're talking about y of n and x of n, where n are all of our samples in time. So not frequency bins, but samples in time. And on the right we have our b vector, b0, b1, b2 as coefficients. You can see how this equation would be generated from this here. We could have any arbitrary number of coefficients. It doesn't have to be 3. Most of the filters that I've worked with here so far have been 6 total coefficients, 2 3-element vectors. Now if we solve this difference equation for y, which is the output of the system in the time domain, then we'll see that y is dependent on both x and also on y. So it's dependent on past values of y, which is why IIR filters are infinite impulse response filters. Because no matter, even if your input x goes to 0, you still have these residual components of the output that are dependent on past values of the output. And so, unless your coefficients a1 and a2 don't exist, which by the way would mean that you didn't have an IIR filter anymore, that means you would have a finite impulse response filter. So as long as a1 and a2 exist, you have an infinite impulse response filter, and that means that even if x goes to 0, y is still going to be dependent on past values of itself, and so as long as y was never 0, then it will never truly decay to 0. If a1 and a2 are some fraction, then y will decay, and it will, in many cases, decay to the point where it's relatively trivial. It's close to 0, but it will never truly be 0. So you can imagine if y is 1 and a1 is 1/2, then at the next point y would be dependent on 0.5 times 1, and the point after that it would be 0.5 times 0.5, and then 0.5 times 0.25, and 0.5 times 0.125, if none of the other terms here mattered. That's what you would be left with. So you can see that it would decay as long as a1 and a2 are fractional, but it would never truly reach 0. So if we go back to our frequency domain representation here, I talked about dividing the output by the input so that the shape of the stimulus doesn't matter. But if the stimulus was flat, if we knew for certain that X was white noise, for example, that means it would have equal energy per frequency, and there would be no difference between Y itself and Y divided by X, because you'd essentially be dividing Y by 1. So in the time domain, our impulse response, which is our time domain characterization of a system, we want to use an impulse as the input, therefore generating an impulse response. An impulse is also referred to as a Dirac delta function. This is lowercase delta. We're used to seeing uppercase delta, which is a triangle. We use that so much, we even sometimes use the word delta as a synonym for the word change, but delta has other uses in mathematics. So this is a lowercase delta, represent this impulse shape, which is a 1 here and then 0 everywhere else. And this impulse response in the time domain has a flat frequency response. So we're stimulating our system with equal energy per frequency. And if, and only if, we're stimulating our system with equal energy per frequency with this impulse response, I can rewrite Y as the impulse response. If we're stimulating our system with an impulse, then the output is the impulse response, obviously. So if X is some other arbitrary input, I can't rewrite Y as H, but if I rewrite X as delta, then that means Y becomes H. And so I can use this to directly compute my time domain representation of the system, which is the impulse response, H of n. And so I'll go to Octave here now. Now I'm going to generate these coefficients here as reference, and then we will both compute the transfer function directly in the frequency domain, then use an inverse FFT to move to the time domain to look at the impulse response, as well as we'll compute the impulse response directly in the time domain first, and then use an FFT to move into the frequency domain and compare those 4 things, essentially. So I have my coefficients. I'm going to create a frequency vector, which is going to go from 0 to fs minus 1. Now, when we're working in the frequency domain, it's easy to forget about the fact that many times we're looking at only half of a spectrum. The full frequency spectrum is essentially, quote-unquote, like double-sided. It has a mirror image of itself. The second half is a complex conjugate of the first half. And we very often throw the second half away. We don't need to look at anything above the Nyquist frequency, essentially. But all that information is necessary in order for our FFTs to work out properly, because if we started in the time domain, we computed some FFT, and we threw out half the points. If we want to move back in time with an inverse FFT, we need to use those points again, the points that we would, in many cases, throw away. So that's why my frequency vector is not defined from 0 to Nyquist, but it's defined all the way up to fs minus 1. So I still have fs points. And that's because I started at 0, and I'm going to fs minus 1. So from there I create my frequency vector, and then I'm just directly computing my transfer function here. I'm also using this kind of canned function, which is very useful in general. I can use it to compute this many points. The third argument is the number of points. The first 2 arguments are your coefficients. And suffice to say that the result from using this is the same as the result from using this. What I'm doing in this line is essentially what's going on under the hood here. This is a convenient shorthand for a lot of cases, though it won't work for what we're doing here. So now that I've computed the full double-sided spectrum, I can inverse FFT that to generate an impulse response. So I have labeled here H1, capital H1, as my frequency domain representation, and then the inverse FFT is little h1, which is the impulse response. I'm creating a Dirac delta function by defining it as 0 everywhere except for at the first point. And then just because we have this annoying, we're referencing some past samples, but as of the first sample, no past samples exist. So they're essentially 0, but I can't call on a negative index of a vector, so I have to have these if cases here until we get to the third index. I need to essentially force some of these terms to go to 0. Otherwise I would just get an error for referencing the -1 index, which I just know is 0, so I'm putting it there by hand. So for n equals 3 and on, I can just use this function to compute the impulse response. And now that I have, I'm calling this h3 because I referred to the transfer function computed by the frequency function as h2. So in the frequency domain, I'll plot h2. The reason we can't use this is because it doesn't give me the full double-sided spectrum, and so I can't move back in time, which was kind of my point earlier. So because H2 doesn't have the full double-sided spectrum, I can't use it to move back to the impulse response. So we'll see H2 in the frequency domain, but we will not see it in the time domain. So I'm going to create large H3 as the FFT of small h3. And hopefully that will run. Get some warnings, but no errors. Good. Okay. So there are 3 lines on top of one another here, and you can see back my filter definition was 1000 hertz, Q of 1, and 6 dB of gain. So at 1000 hertz, I have 6 dB of gain in the frequency domain. Everything looks good. Because of the log scale, everything is compressed, but this spike here is essentially the same as this. If I was plotting this on a linear scale, you'd be able to see the, well, you'd kind of see the inverse of it, but you'd be able to see the mirror imageness that's going on here. So Nyquist is about here, so everything that happens from Nyquist and below is also happening from Nyquist and above. It's just compressed because of our log scale. And here we have 2 lines on top of each other, a red line and an orange line, which are a blue line and an orange line. The blue line is the impulse response that I computed from inverse FFTing the transfer function that I computed. And the orange line is the impulse response I computed directly. So, obviously this reciprocity needs to exist, but doing it out by hand and seeing it for yourself kind of makes you feel warm and fuzzy inside. So that's essentially everything. Again, on the top we have the transfer function that we computed directly. We have the transfer function that's the output of the freq-z function. We also have a transfer function that's the result of having directly computed the impulse response, taking an FFT of that impulse response. And all of those different things agree with one another.